my name is Isabel Wang. I'm a rising senior at Oakton High School, and today I'll be talking about the role of exosomes in HIV proliferation. I'm currently researching this topic, so I wanted to give a background on it to explain why it is so crucial to investigate. Before I start, I'll talk a little bit about myself. Again, I'm a rising senior at Oakton High School in Vienna, Virginia. After high school, I hope to major in biology or healthcare administration and go on the pre-med path. I'm currently doing research on this topic at George Mason's ACIP program. Additionally, I am making medical illustrations for Heal for Health, where I am part of a medical book project. I am also a volunteer at Inova Fair Oaks Hospital, and I'm actually going into my third year as a volunteer there. Lastly, at school, I am a DECA competitor, part of the tennis team, and am an officer for the MedLife, Healing Through Hearts, and National Art Honor Society clubs. First, let's talk about the basics of HIV. HIV stands for Human Immunodeficiency Virus, and it started as a pandemic in 1981. It's a retrovirus, meaning it integrates its genetic material into the host genome. It mainly infects and kills off a type of immune cell called a T helper, and extreme infections result in drastic T helper cell depletion, which is known as acquired immunodeficiency syndrome or AIDS. Currently, the most popular and efficient treatment option is something called combination antiretroviral therapy, or CART. It involves the use of multiple antiretroviral drugs. And there's many drugs that fall under this category, but they all essentially suppress HIV replication by hindering various stages of its life cycle. So while combination therapy has significantly improved HIV patients' lifespans and well-being, it is still not a definitive cure. And in fact, there is no actual cure, which is evidently a problem in the larger goal of ending the HIV pandemic. I will shortly get into why combination therapy cannot cure HIV and how exosomes play a part in that. The global impact of HIV is incredibly severe. As of 2022, the virus has killed up to 40 million people. In 2022 alone, 39 million have been infected, and cases of severe infection or AIDS have also been reported in more than half of the world's countries. This is a visualization of the prevalence of HIV infections. Darker and redder regions on this map indicate a higher number of cases, and the darkest red here stands for case numbers of up to 50,000 or more. And as you can see, many countries are in red, especially in Asia, Africa, and South America. I also want us to take a look at the consequences of HIV infection really quickly. So HIV can develop into AIDS, and when AIDS develops in patients, it acts as a gateway to a large array of other severe diseases. Here I am showing you the most common ones, and even then there are quite a few. They range from things like bacterial infections to cancers. As you can see on this list, there are conditions like salmonella and lymphomas mentioned. Like I said before, combination therapy is not a cure to HIV. Additionally, the treatment regimen requires extremely strict adherence, otherwise there is opportunity for the virus to come back during and after treatment. Exosomes are a potential avenue that HIV can take to do so. So combination therapy actually cannot reach certain areas and cells of the body, and this group of regions is known as the latent reservoir. As the name suggests, these areas hold genetic information for HIV, but do not use it to create viruses. The most notable parts of the reservoir include the immune cells, brain, spine, and lymph nodes. Combination therapy also does not mediate exosome release, and this means that when the latent reservoir releases infected exosomes into the body, they can merge into other cells, like uninfected cells. This is a mechanism that keeps a constant low level of viral transcription and spreading, which can ultimately result in viral rebound. So this brings up the question, how exactly do exosomes from HIV-infected cells transmit infection? Well, to understand that, the function of exosomes must be comprehended first. They're a type of vesicle released by cells for communication and are taken in by recipient cells. They carry cargo like proteins, nucleic acids, and lipids, which are carefully selected by a set of sorting proteins called the escort pathway. However, HIV is able to hijack these proteins and get them to transfer viral materials into the exosomes as well. And most commonly, this is viral RNA and proteins, but not the whole virus. When these materials are transmitted to recipient cells, however, it can prime the cells for HIV infection, cause infection, or if the recipient cell is already infected, activate it from latency. So let's focus on some of the constituents and exosomes that facilitate this pathogenic effect. I want to focus on RNAs, specifically TAR and genomic RNA, because both of them have levels in the thousands and millions inside exosomes from infected cells, like the latent reservoir. Their numbers can even increase under combination therapy, which can be seen in this chart right here. I'll start talking about TAR RNA first. TAR RNA, or transactivating RNA, is a short hairpin-shaped region near the start of HIV's genetic code that activates transcription. So incomplete transcription of full HIV RNA is pretty common, which is why TAR can exist on its own. When TAR RNA is transferred to uninfected cells, it preps the cell for HIV infection by suppressing apoptosis, so that when the cell actually is infected, it doesn't die off, but instead stays alive so that the virus can take advantage of its cellular functions to replicate itself. And for infected recipients of TAR RNA, it can activate a signaling pathway called NF-kappa B, which has been shown to cause latently infected cells to start transcribing HIV again. So genomic RNA, secondly, and on the other hand, is not as abundant as TAR RNA. However, it is much more dangerous and in a more straightforward manner. This is because it's the full-length code for HIV, or the blueprint. So when this is transferred to uninfected cells, these cells basically gain all the necessities and materials to create new virus particles. In other words, these cells now have the ability to partake in HIV replication. So clearly, exosomes are a problem when it comes to complete eradication of HIV in patients undergoing combination therapy, as exosomes released from the viral latent reservoir have potential to trigger infection all over again. HIV cannot be fully suppressed in humans if this microscopic activity persists. So, what can be done about it? I mentioned previously that HIV manipulates the sorting escort proteins to put viral content into exosomes. So, a drug should be developed to stop the virus from hijacking the sorting process. This will ensure that no dangerous viral material can be transferred through exosomes. However, it should be noted that if such a drug is created, it needs to be tested for compatibility with antiretroviral drugs, because only when they are taken together can HIV replication be completely blockaded. Often, taking multiple drugs at once can result in adverse side effects or conditions. So it's imperative that these drugs can work in harmony. Hopefully, this type of drug can be developed in the future, so it can be the finishing touch in ensuring complete HIV suppression, and so that it can give more flexibility in treatment administration for HIV patients. Here are the sources that I've referenced, and that brings me to the end of my talk. Thank you so much for listening. I hope you were able to expand your knowledge of HIV as well as my research and why it is important. I have attached my email so that if you have any questions, you are welcome to reach out. Again, thank you so much for listening.